So maybe I'll just start off by making a little bit more precise something that I waffled about last time. So let's say a bridge trisection is reducible. And we'll make this a dual definition. Two very related notions, reducible and splittable. If there is a curve delta in the complement of the bridge points on the core of the bridge sphere, such that I can always get gamma and delta confused.
Simple delta.
Yeah. Simple closed curve. Good. Such that gamma is the boundary of DI for Jason gets me, embedded disks D sub I in these three balls. Satisfying, well, in the first case, they satisfy that DI intersects the tangle in a single point. And then respectively, DI intersects the tangle not at all for each I in C3. Okay, so otherwise, the bridge trisection is irreducible, respectively, I guess, unsplittable? I think I wrote non-splittable. Should we take a quick vote?
No.
Non-splittable. Okay.
That was a vote.
The vocal minority. Okay, reducible, splittable, irreducible. Okay, I thought we irresplittable. Okay, so I kind of drew a picture of this. Maybe I'll just illustrate with one of these. Maybe I'll illustrate reducible, right? So the idea is that you have your sphere, and you know, you've got some bridge points here, and you have your curve. Delta is sitting on the sphere, and it kind of goes, you know, it's going around the sphere this way, and it bounces disk D sub 1, which intersects T1 in a single point. And there's other things going on with T1, but that's the key thing. And then the same thing happens in all three tangles. So we have something like this. And we have something like this. Okay. And so what I talked about last time, if we take the connected sum of two tangles, we have exactly this sort of reducing curve. And if we take the split union of two tangles, we have exactly this sort of splitting curve. And to make precise the remark, because I think this is interesting to me. I think this is kind of important. This reducing or splitting curve, delta, encodes a three sphere, and this is also true if we were to have such a curve in a trisection. It encodes a three sphere Y sitting inside our four manifold, such that, well, the first thing we have is that Y intersects sigma in delta. Y intersects each of the BI's in this disk PI. And then finally, there's y intersect the zi's is a 3-ball for each I. Okay. So we can think of delta in y is the unknown with fibers, the disk fibers given by the di. Okay, and then I'm going to make a definition which will seem a little out of place until we look at some more examples, but now that we know what it means to connect some bridge trisections, we'll say that a bridge trisection is standard if it is a connected sum / split union of bridge trisections of, let's say like that, well, of bridge trisections with b less than or equal to 2, or 3, sorry. So this is going to seem a little mysterious until we talk about what we're going to talk about next, which is the classification of bridge trisections up to bridge number 3. But somehow the way I prepared this kind of got put in this order. Okay.
Do you mean that the whole B is less than 3 or the pieces?
The pieces.
Okay.
Bridge trisection is standard if it is a connected sum such split union of bridge trisections whose who have b less than or equal to 3. That's a little bit better. I don't remember how to do that. Okay. All right, so let's get back to talking. Let's get back to talking about examples now, and let's try to justify this claim that somehow we shouldn't care about bridge trisections where b is less than or equal to 3. Okay, so first let's consider the case where b is 2. So I think I'll just go ahead and draw these, or maybe I should maybe I'll do it like this. Proposition. There are precisely 6 bridge trisections with b less than or equal to, with b equal to 2. Okay. And of course, there is 1 with b equals 1. Everybody's seen that guy. Okay, so there are 6 bridge trisections with b equals 2. So should we draw them? Minus 1. Some of them we've already seen, I think. So almost all the time, we're going to assume that our first tangle is that guy, and then the second tangle is going to be either one of these two based on the value of C1. Okay, so from what I've drawn so far, you can figure out what C1 is, and then the last pictures are going to look like this. And then over here we have this. This will be fun for you guys to copy down. Okay, and so, so let's just, now that I've drawn these, let's think through what they are. So this first one here is, what's the complexity of this first trisection?
1, 1, 1, 1, whatever you say. I mean, 2, 1.
Bridge number is 2.
Yeah, bridge number is 2, and there are 2 components in every.
And there's 2 components in all of them, so it's balanced here. So maybe we'll say balanced 2-2 bridge trisection. And we've already discussed that this is a bridge trisection for the disjoint union of 2 spheres. Okay, and then this one we've already seen is also balanced 2-1 bridge trisection for P plus. And this one is for P minus. So these 3 we've talked about before. These 3 I don't think we talked about before. Okay. So, well, what are they? What type of a bridge trisection is this guy? Obviously, B is 2. What are the values of C?
2, 1, 1.
Yeah, so the union of the first 2 is 2, but then this one is 1 and this one is 1. So it's a 2-1-1 bridge trisection. So it's unbalanced. And then from these bridge trisection parameters, can you tell me what surface it is?
The answer is yes.
Oh, yeah, the answer is yes.
Yes.
Oh, maybe I'm getting a little confused about having told you something. We do know how it corresponds to like the number of cups, caps, and bands, right? We talked about, no, we haven't talked about that. That's what I'm talking about today. Okay. The answer's still yes. So, okay, what is it? What does anyone know about this guy?
So it's crossingless, so it has to be unknotted
Mm-hmm. And
has to, or
orientable.
orientable.
Yeah. And then, so which unknotted orientable surface is it?
Euler characteristic.
Yeah. Yeah, it's good. So we know it's unknotted, orientable, and we know the Euler characteristic is the sum of the C's, 1 plus 1 plus 2 minus the B is 2. So it's an S2. So this is an unbalanced unbalanced 2-bridge trisection for the unknotted sphere. And then these are all clearly, they're the same, but they're also different because when we consider trisections, we consider, I guess, well, we consider them with a fixed ordering of their pieces. And so this one is a 2-1-2-1 bridge trisection, and this one is a 2-1-1-2. So these bridge trisections are distinguished by the number of disks in each sector. They would clearly be like diffeomorphic by some sort of diffeomorphism that permutes the indices.
Right. So why don't you have more for the permuting the P plus tangles? I guess
Well,
last time we saw you can do the break.
you can undo them, yeah. So that's right. So you might, that's right. Let's just revisit that. That's a good question. So let's say we sort of cyclically permute, the pieces of P plus. So we get this. Okay. Right, and then what we want to do is do triplane moves to get to figure, I'm claiming that this is one of these. All right, so that means we should be able to do triplane moves to do that. Well, our best bet is to probably undo this guy. Oh, that didn't work for a while. Oh well, getting closer maybe. Oops. I did the wrong thing, didn't I? Okay, so that was the wrong thing to do. Because that didn't really help us. So now I want to get this gone. So the really bad thing to do would be to do that again, right? So let's do something different. Let's do this. So that is in the wicket group, so we're good there. and this undoes this crossing, and it becomes this. And then over here we get this.
What did you just show?
Yeah, what did we just show? Good question. We showed that the bridge trisection corresponding to this, so this bridge trisection is isotopic to this bridge trisection. Because their diagrams are related by triplane moves. And so Jason's question was, why didn't I list permutations of these tangle options? And the answer is you can always make the first two standard. And so anything we encounter can be encoded in this list.
Also, I guess a better question maybe would have been, why are you distinguishing between the two on the bottom, right? How do you know those are different?
Well, these are different because there would actually be no way for me to, did I do it right? No, that's right, yeah. Yeah, the problem here is, actually, maybe there's a better way. Let me fix this one. Let's do some moves. Yeah, I think I did this. No. So there was no reason for me to make this tangle look like this, I don't think. But let me try it. Well, what are we doing?
The answer to your question, Jason, is that the numbers 2, 1, 1, 1, 2, 1, 1, 1, 2 are different.
So by doing triplane moves, you're not going to change the number of disks
Right.
in the second sector.
Yeah, that's true.
But so this probably can be drawn with the wickets here. And then these two, I mean, shouldn't it just be this? Let me just guess. At the board in class is not usually the right time to just guess. So, I guess I could have just done this. Why didn't I just do that? That's better. Now I mean, I guess the reason I didn't do it is because I wanted to see that these were clear permutations of each other, but I'm a little bit happier with this. So the point is, we can always pick the wickets for our first tangle, and we can always pick our second tangle to have no crossings so that the union is giving the right number of components according to C1. So there were only 2 times when C1 was 2, and in that case, we picked the wickets again. In the other cases, C1 was 1, so we picked the infinity tangle versus the 0 tangle. Okay.
Can you see the diagram for S2 as the equal to P2? Can you see anything like that?
You want to list those maps that are double covered.
Well, let's be a little careful. I mean, the double cover of this would be CP2. So it'd be, you could lift it to RP2 lying in CP2. I think you're thinking of something like take S2 in S4 and quotient to get RP2 in RP4. Maybe something like that.
Yeah, I guess, yeah. I just had forgotten that this is on the same side of S4.
Right, yeah.
I was just S2.
Yeah, so to answer your question, I'm not sure what the natural map from the RP2 in S4, or from the S2 in S4 to the RP2 in S4 is. And I don't know how to do this in RP4, but that would be an interesting thing. Add that to the list, Dave. All right. Okay, so I wrote out in the notes a proof of this proposition. It's like almost a page long. And it depends on something that I haven't proved, which is this sort of classification of rational links. So if you think back to the second day of class, on this board here, I drew this double unit square with a bunch of slopes on it, and then I quotiented these rational links. Well, if you want to classify So maybe I'll just sketch the proof I do that. And then the main input will be a black box, and then the details will also be a black box. So if you want to classify two-bridge trisections, again, you can always assume the first one looks like this, and let's just assume case one, let's assume that C1 is 1. So that means the second one can look like that, and we get something over here. We get something over here that looks like this. So alpha 3. Right? And so what we see is that we have T1 union T3, say, I guess I will do it like this. We have T3 union T1 bar and T3 union T2 bar look like, they look like this. Okay, so these are two bridge lengths. Okay, and we want them to be either an unknot or an unlink. Okay. And so you can appeal to the classification of rational links, two bridge lengths, which is due to Conway. And it's really, I mean, it's really just related to the classification of lens spaces via double bridge cover. But so you appeal to Conway, and that restricts which two bridge tangle this third piece can be. And you just kind of list the options, and you get however many options there are with C1 equals 1. You get 4 options. Okay. With cases depending on whether each of these unions is an unlink or an unlink. Okay. And it's straightforward to do. And then you do the case of C equals 2, where you're asking for this. Okay, so I don't think I want to spend any more time on that. But like I said, I wrote out the details. Okay. So then the next thing to mention is something which I'm not going to talk about in detail for a different reason. There is a unique, irreducible three-bridge trisection. Okay. So this is a result of Alex and I's, although we didn't really prove it. Well, so okay, here's how we might have proved it. Well, this was originally proven using trisections. So it was originally a result about genus 2 trisections, or 4 trisections, let's say. And using a result which I think I mentioned in class earlier, this result of Homo-Ochiai and Takahashi, which has, Homo-Ochiai and Takahashi originally proved this result about genus 2 Haggard splittings of S3. But I've mentioned this in class because it's actually equivalently, it's a result about 3 bridge splittings of the unknown. Okay, so that's why the result is familiar from this class, is because I mentioned that every shadow diagram for a 3 bridge splitting of the unknot has a wave, a shadow jump that reduces the number of intersections. So the result for Haggard splittings is that every genus 2 Haggard splitting of S3 contains a wave, which is a slide that reduces the number of intersections between alpha and beta curves. And so you take this as input, and then you basically do 40 or 50 pages of combinatorics and note taking and note keeping, and kind of you force it to fall out that there's a unique irreducible genus 2 trisection. But of course, as we'll see later, genus 2 paragraph splittings and trisections are equivalent to 3 bridge splittings and trisections. And so this result immediately descends to give us a result about knotted surfaces, namely that there's a unique one with bridge 3. So we didn't prove this using shadow diagrams and jumps and everything, but it seems like you could do exactly that, which I don't know. Maybe it would go through almost exactly the same way, or maybe it would be a little easier or harder to do it with shadow diagrams. I don't really know the answer to that. Of course, we've seen this diagram already, but might as well draw it. I think I convinced myself that there's no way to draw this without crossings so that this is the wickets. Which seems weird, but I think it's true. Okay, so maybe you could try to do that. So this is the one diagram that I don't draw the wickets here because I don't think I can draw this without crossings if this is the standard picture, which is kind of weird. But anyway, this is a 3-1 bridge trisection of the unknotted torus, as we've seen before. I guess we call it unknotted genus. So this is then a complete list of bridge triangles. For completeness, let's look through this. Okay, so on the board you see the 8 bridge trisections up to b equals 3. Okay. And that's why, so this motivates the fact that, okay, so let's take these to be our sort of standard pictures, and then anything you can obtain by taking split unions or connected sums of these pictures, we'll call that trisection to be standard. I guess I probably also want to include stable perturbations in that, but we haven't talked about that yet. Note to self. Okay. And then maybe I'll just say out loud that we'll see soon that once you get to b equals 4, you actually get infinitely many distinct bridge trisections. There's a whole list of them. You've already seen one, right? We've spun the trefoil and gotten a 4-bridge trisection for that knotted 2 sphere. And really, we could spin any 2-bridge knotted link and get a 3-bridge trisection. But before I talk, so in order to prove that those, in order to talk about that, I think we want to first talk about fundamental group and stuff like that. So I'm going to switch gears a little bit and work towards that. Any questions about the things I just erased, or this sort of classification of low bridge number examples?
I have one question about how to see orientability of the surface from the diagram. So I get how we understand like the Euler characteristic and how we, if there are no crossings, then our surface would be unknotted. But what about orientability? How can I see that from the from the diagram?
So one way you can think about doing it is you can take one of your bridge points and you can orient that point. And then what you can try to do is you can try to extend that orientation on that point. So it's like that's like picking a local orientation on a surface. You can try to extend it to the rest of the spine of the bridge trisection. Do arrows point from negative to positive or positive to negative?
Negative.
Negative to positive. Okay, let's make it negative. Just if I want to draw this arrow this way. So if I want to orient this consistently, then that's going to give me a plus at my second point. And over here, I have the same the same information, but that now lets me extend this even further. And this, right? And then now we're done. So now I've assigned an orientation at each point by following some path of arcs in the spine, and I'm done. And so if it's consistent with all of the arcs in my picture, then I'm in good shape. So the red guys can be oriented to match this. The blue guys can be oriented to match this. And the green guys can be oriented to match this. So that tells me that I've now oriented the spine of my bridge trisected surface. And in particular, I have an orientation on each of the boundary links in each of the sectors, so I can extend it over the discs. If I had tried to do this with a Klein bottle, it would fail. Does that answer your question?
Yeah, yeah.
Okay, good. Okay. Anything else? Okay, so what I want to do next is rewind a little bit and kind of go back to thinking about the connection between bridge trisections and banded link diagrams or you know, Morse functions on surfaces in normal form, that kind of thing. So we kind of talked in detail about how to go from a surface in normal form. You get this banded link, you put it in bridge position, and then you build your trisection that way. That was the existence of trisection. So now let's think about how we go backwards from a bridge trisection to a surface in normal form. Okay, so let's see what this looks like. So consider a bridge trisection, and you know, we're going to be interested in the spine, so let's just make sure we know how we're keeping track of the spine, sort of standard notation. And let's consider the links, or the link, let's consider one of the links. So I guess what I'm doing here, I could choose I to be 1, 2, or 3. Okay, so it'd be sort of important that there are 3 different ways of doing this. So let's pick one of them. So for I and Z, let's consider the link Li, which is the boundary of the ith disk system. And let's consider the shadows delta I plus 2 star for a membrane system, I guess delta I plus 2 for the I plus second tangle. And let's consider a subset Y star of shadows of these shadows, such that a couple of things are satisfied. So we want to work backwards to essentially get a banded B-bridge splitting. So what do we want Y to satisfy? Well, the number of shadows that we choose out of this collection of shadows should be B minus the I plus second complexity, so the number of disks in the I plus second system. What do you think about this? This is I plus 1. Nothing like adjusting something like that on the fly, but I think that's supposed to be I plus 1. Let's keep an eye on that. Okay, so the first thing is that tells us how many shadows we should pick, but that's not very helpful because there are lots of different ways to choose that many shadows. The second condition is that we want delta I plus 1 star, so the shadows for this I plus first tangle union the selected shadows Y star should be an embedded collection of arcs in sigma for some membrane system, delta I plus 1 for the I plus first tangle. Okay, so we're choosing very carefully some subset of the shadows for the I plus second. So if you want in your mind, you can think about I being 1. So then we're looking at the union of the link given by the union of the red and the blue tangles. Then we're considering green shadows, or gamma shadows. And we're going to pick some of the gamma shadows, but the gamma shadows that we pick should be compatible for some membrane system for the blue tangle. The green shadows should be compatible with those blue shadows. Okay. Looks like I have a picture here. Okay. So all the interesting stuff in this setup is happening in 2 of the tangles, right? The I plus first and the I plus second tangle. So so we might as well assume that they have no crossings. What do they do? Oh, okay, we could make our lives easy by assuming 1, 2. Bear with. Oh, we need more. Surprising number of dots on this. Still don't know that dots. The past Jeff thought that this example needed to have a lot of arcs. Okay, so this is an example of what the union, so this, in this rendering here, this is Ti plus 1. Okay, good, I'm glad I did this example. And now I think I want to go back and change this. Great. Yeah, I plus 1. And okay, I believe that this should be a picture of L I plus 1. And so what exactly are we looking for? Well, the green shadows that we might pick then would be something like maybe we pick this green shadow here and this green shadow here and this green shadow out down the back, and let's come over here, this one, and maybe then we also pick this one down the back. Okay. And so first of all, let's see if the combinatorics work out right here. So in this example, B is 1, 2, 3, 4, 5, 6, 7, and C I plus 1, which is the number of components here, is 2. So that means the cardinality of Y star, please, should be 5. Okay, good. So far, so good. And I guess it's not, maybe it's not immediately obvious, but let's just, if you just sort of draw in the sort of blue shadows, what do you see? You sort of get one here, right? And then this one comes over here, this guy, and then maybe this one goes all the way around the back. This isn't too bad. And so what do we see? We should see an arc, right? This is one arc. You see that? So each component of this link is going to give us a single arc of Y star of the selected shadows from the third tangle and the nice shadows for the second tangle. Same thing happens over here. There's this little disc here and this little disc here, and this, I guess, this disc, which would go around the front. That, and again, we get an arc. So you'll notice exactly what we're doing is we're choosing all green shadows except one per component of L I plus 1. And if we chose all of the, if we make the green and blue tangles look as nice as possible, then we can choose green arcs and blue arcs that give us embedded curves in the bridge sphere. But we don't want embedded curves, we want embedded arcs, and we want sort of a maximal number of them, so we throw away one arc from each of those embedded curves. We throw away one green. Okay, so this is the setup that this is all meant to realize. And this is the setup that what sort of the whole banded bridge splitting thing was meant to ensure. Okay. So I think I've, all right, so what is the claim?
You chose that carefully enough so that they're all dual. So that green disk is.
It's sort of automatic.
It's all that.
Yeah, yeah, it will be automatic because they're arcs, right? Each arc is going to look like, each arc, what did I pick? So much. My blue shadows are purple and my green. Actually, it should be and purple and black. So each arc is going to look like that, right?
That doesn't seem like what you drew. What do you mean by that?
Oh, maybe it's the other. Oh, yeah, no, I just didn't draw enough in. Right, so there's the arc of shadows here. Where does it start? It could start here, and it goes blue, green, blue, green, blue, green, blue, just like this. And so it is true that each yellow guy, which is corresponding to Y star, which is going to correspond to our bands in a second, is in fact dualized by a membrane by a purple-blue membrane. This is like one of those tests where you. Anyway, I think I'm passing so far. You guys done this? You see the words? See the words written in different colorings. All right, what is the claim? The claim is that given this setup, if I take, okay, so let's let B inside YI, LI be surface framed bands for LI with core, so that the cores of B is these Y stars, right? So we've got this kind of thing going on, and we have this Y star piece like this, and by choosing the surface, the normal framing to the surface, we get this transverse band. So that's going to be our B's. And then the claim is that YI, the three-sphere YI, together with the unlinked LI, together with the bands, which is naturally split as, I guess, T1, B1, T1 union along sigma X, Y star, B2, T2. Am I in the right indices now? Yeah. Oh, except I switched, this should be I. And this should be I plus 1. Because we're carefully doing this in generality for some reason. This is a banded B bridge splitting with realizing surface S, which is the original bridge trisected surface length. So the claim is that by very carefully choosing these yellow arcs, these Y star, I've actually chosen a collection of bands for the link Li. Let's see what I want to say in support of this. So to prove this, it suffices to show that that the result of taking the I plus first tangle, which is the blue tangle, and resolving the bands after we perturb them into the blue tangle as we do, gives us our third tangle, our I plus second tangle. And the reason for this is because, so we've now taken our bridge trisection and we've extracted a banded link. And so what we could do is we could try to build a bridge trisection from this banded link. And we want to get the same thing we had before. And so what do we need to check? Well, we know resolving these bands for the second tangle will give us a third tangle. If it matches our original third tangle, then the spine of the bridge trisection is right. And so necessarily the third piece, the pieces will look the same. I mean, the caps and the cups are kind of automatically the same. The piece encoded by the bands, the second section will follow along once we know that the boundary link is actually the same bridge splitting at the same boundary link. Okay. So I kind of mentioned this out loud, but I'll just say it. So for each component J of Li plus 1, we pick Bj minus 1 shadows coming from the tangle Ti plus 1 intersect J, where Bj is the bridge index of J with respect to the sphere signal. So it's exactly what I did over here. We pick all but one of the green. Oh, same number. We pick all but one of the green shadows. I feel like the number's still off. Nope, that's right. Okay, everything's fine. So then if we think back to the way that we got our third tangle from the banded link in the existence proof of trisections, is that each arc, let's see if I can remember this picture. We had something like this. Yeah, let's just draw this. So we've essentially arranged this picture, and if you remember the existence proof, where did the green tangle arcs come from? Well, we got one for each band, right, coming from these Y star. So we get one shadow or say strand of Ti plus 2 from each component of Y star. Okay. And then the final component, we get one that looks like this. Plus one more. And the one more we get is, so remember, if we had linked this up to be a full curve, it would have looked something like this, right? And so we get green shadows and green strands from each component of Y star. And then we also get another one, which is a push off of the union of that arc. And that's parallel to the original guy that we discarded. Okay. And so I I don't claim that was perfectly understandable, but I do claim that I've said enough that you can conclude that there is a way to extract a banded length from a bridge trisection using this sort of algorithm, such that if you immediately tried to reconstruct the trisection, you would get back. Okay, and we're out of time, so I'll stop. So next time we'll talk about, so yeah, this is actually, so the key thing that made this really confusing but also important is that we could have started with I equals 1, in which case we're looking at, featured prominently was the blue and green kind of pairing. But if we had picked I equals 2, then it would have been the green-red pairing that was interesting. So we use this threefold symmetry of the trisection setup to extract different banded lengths. And that'll give us handle decompositions of our surface with different numbers of handles of each index. And so next time we'll explore what kind of the cool things that tells us. Any questions? Made it to another week.